In this short animated video, we'll break down what is Bayes' theorem in statistics in the simplest possible way using some intuitive examples. So sit back, relax, and enjoy this video. Is 99% accurate always 99% true? Let's see this. Imagine there are two bags in front of you. Bag A has 3 red balls and 1 blue ball, while the bag B has 3 blue balls and 1 red ball. Now, suppose you are blindfolded. Without looking at the bag, what is the probability of picking a bag A and bag B? Since both has equal chance, there is a 50% chance that this person will pick bag A and 50% chance that he will pick bag B. So far, everything seems right. Next, suppose the chosen bag is bag A. Now, a ball is drawn from this bag, and the chosen ball turns out to be red. And this is where the things will get interesting. You know the ball is red, but you don't know from which bag it came. It came from bag A or it came from bag B. So let me ask you another question. What is the probability that this red ball came from bag A? Most people will guess 50%, some will say 75. Others probably will not be sure. But this simple question reveals one of the most powerful ideas in probability and statistics. This is called Bayes' theorem. Let's see now how this works in real life. Now let's take a step back. Before any ball was drawn, both bags were equally likely to be selected. Bag A has 50% chance of being chosen, while the bag B also has 50% chance of being chosen. At this stage, we don't have any additional information. This initial belief is our prior probability or simply the prior belief. But then something important happens. We pick a ball from bag A and it turns out to be a red ball. Suddenly, we have this new information. This red ball becomes our new evidence. Now ask yourself, which bag is naturally more likely to produce a red ball? Bag A contains 3 red balls out of 4, while bag B contains only 1 red ball out of 4. So after seeing a red ball, does it still make sense to believe both bags are equally likely? Not really, because a red ball is much more likely to come from bag A than from bag B. As soon as we observe this new evidence, our original belief starts to change. And this is exactly where Bayes' theorem comes into picture. So Bayes' theorem is simply a method for updating the belief when new evidence becomes available. Think of this as a three-step process. Step 1 is prior information. This is what we believed before seeing any new evidence. In our example, bag A had 50% and bag B also had 50%. Step 2 is evidence. We observed new information. In this case, the evidence is the selected ball is red. In real life, evidence could be anything: a medical test report, a customer complaint, a quality inspection report, a sensor reading, or could be anything else. Third step is the posterior. Now we combine our original belief with this new evidence. The result is the updated probability called the posterior probability. This posterior represents what we believe after considering the evidence. And that is the entire idea behind the Bayes theorem. So in one sentence, Bayes theorem tells us how to revise what we believe after observing a new information. How to calculate the probability value using the Bayes theorem. Let us first look at the famous Bayes theorem formula. Everyone would have seen this. At first glance, it looks like a little bit intimidating. Lots of formulas, symbols, letters, but don't worry. Once you understand each term, the entire formula surprisingly will become little simple. So how do you read this formula first of all? It is read as probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. Or if we translate into simple English, posterior is equal to likelihood into prior divided by evidence. Now let's look at each term one by one. The probability of A given B is the posterior probability. This is the updated probability after seeing the evidence. That is what we are calculating. Probability of B given A, this is the likelihood. It tells us how likely the evidence is for our hypothesis is true. Probability of A is the prior probability. This is our initial belief before observing the evidence. Probability of A, this is the evidence probability. It represents the overall probability of observing that evidence. Once these four terms are clear, Bayes' theorem will become much easier. Now let's take a simple example of medical test. Imagine that there is a disease that affects only 1% of the population. We have a test that is 99% accurate and the person receives a positive result. So here's the question: what is the real chance that this person actually has a disease? Most people immediately will answer 99%. But Bayes' theorem tells us to slow down. Before trusting the test result, we need to ask, how common is the disease in the first place? Since only 1% of people have disease, the disease is actually very rare. And that is where the Bayes' theorem comes powerful. It helps us combine the disease rate, test accuracy, and the positive results to find the real probability. Let's work through the numbers and see the surprising answers. To make it simple, let's assume the population of 1000 people. Since the disease rate is only 1%, that means only 1% will get affected, and only 10 people, that is the 1% of 1000, will have disease, and remaining 990 people will not have any disease. This is called the base rate or the prior probability. And this number is extremely important because when the disease is rare, even high accurate result can sometimes produce misleading results. That is exactly why the Bayes theorem does not look at the test result alone. It asks first question: how common is the disease in the population? Now that we know the base rate, let's see what happens when 99% accurate result is applied to this 1000 people. The hidden problem, the false positive. Even a good test can create false positive. So for a true positive means the person has disease and test correctly reports a positive result. While a false positive means the person does not have a disease, but test result still reports a positive result. Even when 99% accurate test, a small number of healthy people still will have test positive. And here is the catch. There are only 10 people with the disease, but there are 990 healthy people. So even a tiny false positive result can create a surprising large number of positive results from healthy people. And that is why the positive test result does not automatically means uncertainty. To find the real probability, we must separate the true positive from false positive. And that is exactly Bayes' theorem help us do. So what the Bayes theorem reveals? A positive test result does not automatically means 99% certainty. But when we combine all three, the actual probability of having a disease after a positive result is only about 50% and not the 99%. This surprises many people, but it makes the perfect sense once we conclude the Bayes result. And that is the key decision of the Bayes theorem. Don't judge probability using the evidence alone. Consider the prior information too. So next time you see a new evidence, don't jump to conclusion. Start with what you know already, combine it with new evidences, and update your belief. That is exactly how the Bayes theorem works.